So our first question, what is physics? And what I want you to do is write on yours. Remember, all notes are Cornell notes style. I want you to write down what you think we are going to study in physics. What is physics the study of? What do you think it is? What do you think it is? And all that. I'll give you a second to write down a few things. So I'm going to tell you, what do you think physics is, or what do you think we're going to study this year? Anyone? Yes, sir. How stuff works, how stuff moves. That's good. Yeah, we're going to do some of that. Anyone else? Yes, sir.
Physical properties of objects.
Physical properties of objects. Yes, we're going to do that. Movement, swinging, periodic motion, stuff like that. Those are all good things. That's a lot of our first semester stuff. But what I like to say here is physics is the study of how the universe works. How the universe is put together, how the universe works, how things, we talk about how things are put together, how things do that. The periodic table of elements, although we use it in chemistry, it's physics. That whole arrangement is about physics, because physics deals with atoms, the basic building blocks, motion, energy. In fact, the shortest definition I know of physics, it's the study of the conservation of energy. This is rule number one of the universe. Rule number one of the universe is conservation of energy. When you look at anything, the first thing, is energy conserved? If it's not, if it appears energy is not being converted, that must not be happening, because you can never not conserve energy. So it's inviolate rules of that. Which means physics is really the foundation. If we think of science as a pyramid, physics is the base of that pyramid. Physics is the least complex of all sciences. You might think, well, what are these guys doing physics, like Einstein and these guys? You have to be an Einstein. No. The ideas are very easy. Yes, the math is difficult. Even Einstein said after they took some of his ideas and put the math in it, he didn't recognize them. The math can be difficult. Remember, we're dealing with concepts, the ideas of physics. The ideas are very simple. So the ideas. And once we build on those ideas, we get a little more complex. It's more complex. Anybody know what is the most complex science? What is the most complex science? One you guys have already had. Biology. Chemistry is in the middle. Biology is the most complex. Let's think about it. When you read in the paper, do you read the discoveries in physics? No. Do you read about discoveries in chemistry? No. Do you read about discoveries in biology? Yes, because biological systems are horrendously complex. One cell organism. We think, oh, that's pretty simple. Not very simple. It's run by a computer that has a longer program than anything we have today. Even though we kind of know what causes some of these things, we don't know how it got there. The coding of it and things like that. Just to think about, at a certain time, it's going to unzip, it's going to make all these proteins, and then it's going to send something out. It's going to make more proteins, and it goes out. And this, think about what's going on in the simplest little cell. Does that sound very simple? No. Very, very complex. This is why, although in physics, I can model almost anything with a computer. This is pretty simple. It may take a supercomputer. It may take lots and lots and lots of hours. But I can do it. Some things in chemistry I can computer model. Biology, forget it. Just too complex. Think of all the systems in your body on that. Think about all the medicines. You read about the medicines that hurt you. It's like, oh, they have this medicine that cures this and does that. It's kind of why medicines cost so much. People realize, like, oh, this medicine costs so much. How dare the company do this? Well, it's kind of like this. Okay, for every medicine that works, think about how many that don't. And they have to pay out for all those, so the one that works has to pay for all the ones that didn't. They only get a short amount of time. This is kind of how this works. because I might have a great medicine that can cure every single disease in my liver. Unfortunately, it makes me go blind. You know, that sort of thing. So this is also why they do animal testing. And even then, it doesn't always work. Sometimes things get through because humans aren't the same as animals. You get most of it. But biological systems, horrendously complex. Now in physics, we build upon that. Once we understand how matter works, we can start putting together in chem, and those chemicals get together and we get life, we get bio. But bio is the most complex of all the sciences. It's very, very, very complex on that. Questions? By the way, if I ever start getting too quick, because I kind of sometimes get worked up on these things and I will get too quick, if you haven't got down, just raise your hand and you need a little bit of time to get some of the notes down. Okay? On that. But we're going to talk about systems of measurement. Systems of measurement. Let's start with the English system. Where is the English system used in the world? I guarantee it ain't used in England. America, yeah, the United States. We are the only ones that really use the English system anymore. It's only used in the good old US of A. You know, we use it. No one else uses it. Sometimes in English-speaking countries you might see parts of it still have remnants on that. The trouble with the English system is that it was developed over time. You know, different parts in different places, and it was combined in. And it's just the craziness of it. I mean, just, you know, all the rules. It's very confusing on that. You know, you think, where did the foot come from? Why do we have this thing called the foot? A foot literally is a foot. And generally it was the whose foot? The king's foot. You know, that was the thing. It's, you know, the king's foot. On that. You know, things like a yard. A yard was like from your nose to your thumb. That was a yard when they measured out cloth. You know, this is, you know, a cloth yard. Now, Grant, you know, if I was a person making fabric, you know, I'd lose a lot of money because my yard's very long. You know, I think if I had some, you know, I would want a worker with very short arms to be measuring out my yard and that sort of thing. You know, so it's on that, but it's like nose to thumb on that. One I love is the acre. Acre, you see a sign, 23 acres ready for development. Well, an acre is a measure of land area. That's what we use that for, is acre. But where did that come from? I mean, no one knows what an acre is. How big is that? But originally it was how much land 2 oxen can plow in 12 hours. Don't ask me why it's called an acre, but that is what an acre was. How much land could 2 oxen plow in 12 hours? There are lots of things, even in length measurement. I mean, it's like we got an inch. Okay, we got 12 inches to a foot, 3 feet to a yard. How many yards? Next thing, we go to a mile. But what kind of mile? There's 2 different kinds of miles. You know that? 2 kinds of miles. Statute miles, which is what we drive on land, 1,760 yards. We have nautical miles, which are 2,000 yards, which is 1 minute of latitude. You know, like your latitude, longitude, your little GPS machines. Well, 1 minute, because you divide 1 degree of latitude into 60 minutes, 1 minute of latitude is 1 nautical mile, 2,000 yards. But even in length, you have things like furlongs, rods, leagues. In the Navy, we used to use fathoms. A fathom is 6 feet. That's where we measure the depth of water. If you look at a nautical chart, the water is measured in fathoms. Fathoms of water. Chain on our ship was measured in shots. How many shots of chain are out? A shot was 15 fathoms of chain. To the Navy ship, on a ship, it's not your anchor that holds you down, it's actually the chain on the bottom that holds you, keeps you from drifting away when you anchor out. The anchor just helps you get the chain out of the chain locker on that. So lots of different things, even in ounces. You know, there's 3 different kinds of ounces. You have fluid ounces, you have dry ounces, but you also have troy ounces. 16 ounces to a pound, 12 troy ounces to a pound. Troy ounces is what we measure precious metals in. Things like that. Pecks and bushels, it's just... You guys want to have to do all that conversion? Remember all that? No. We're not going to do that. We're not even going to convert English and metric. Actually, there's one caveat. If you guys make that horrible mistake of using this side of your meter stick instead of this side of your meter stick, yeah, you're going to have to do English to metric conversion. Let's not make that mistake. You know, remember, there's always a lot more numbers on the metric side than there are on the English side. Okay, on that. So the metric system, System International, the metric system. Now this was proposed as a full system by some scientists in France in the 1700s. And I don't know why they did it. Maybe it's because they didn't want to use the English system. You know, the French don't like the English. Especially in that time. It's like, we're not going to use this stinking English system. I think it's just because they got tired of all the rules. I mean, that's why I would switch. They wanted to make something that was easier to use. But this was developed as a complete system. Developed as this complete system. And they started with the meter. Now, do you think they went out to their farm and just ripped a branch off the tree and said, "This is a meter"? Well, they could have, but they didn't. This actually is a distance on the face of the earth. This meter represents a certain distance actually on the face of the earth. And what these guys did was said, okay, we have the earth, and we have the North Pole, and we have the equator, and we have Paris. Remember, French guys, Paris. And we said we're going to draw a line from the equator to the North Pole to Paris. We're going to take that line. So that's a certain distance. It goes from North Pole to the equator. We have that distance. And I'm going to break that into 10 million parts. I'm going to break that into 10 million pieces. And I'm going to call that one piece a meter. Now, the meter is that 1/10,000,000th of that distance. So 1/10,000,000th. So that's what this is. This is 1/10,000,000th of the distance between the North Pole and the equator on a line through Paris. That's how they came up with a meter. Now, if you look at the meter, you might say things, well, the meter is so many wavelengths of a certain wavelength of light. Yes, they do define that. Is it more accurate? I mean, there is a standard meter. Most countries carry standard weights and measures. You know, somewhere in France, probably in England, and most other countries that use the metric system, they probably have this bar of metal in hermetically sealed containers that's 1 meter. And that would be what we call the standard meter. This is the meter that all other meters are measured of. We don't have a standard meter in this country. We have a standard yard. And the standard yard is kept in Maryland. It's actually where the vice president lives, where it's kept. Anybody know where the vice president lives? The vice president does have his own home, an official home. Just like the president lives in the White House, the vice president has an official home. Does anybody know where the vice president lives? No. Actually lives in Maryland. He lives in Maryland. He doesn't live in D.C., which kind of makes sense. I mean, I'm not sure when they actually moved him out there. You know, in light of nuclear weapons and things like that, you know, it's a kind of good idea. But he actually lives at the Naval Observatory. The official residence of the Vice President of the United States is at the Naval Observatory, which is in Maryland. And that's where they keep the standards, the standard pound, the standard yard, and things like that. Navy had an observatory because, you know, they use celestial stuff, you know, sextants, things like that. Believe it or not, in the day of GPS and all these kind of things, electronic means of navigation, every morning, every evening, there's a guy on a Navy ship, probably a couple of guys who are out there with a sextant taking a star shot, just to verify. You know, when I was in the Navy, they'd only launched about maybe 3 or 4 GPS satellites that time. In fact, it was great. Straits of Hormuz, half the Straits of Hormuz had GPS, half didn't. So which caused problems sometimes on that. You guys don't know what Straits of Hormuz? That's this waterway that goes between the Persian Gulf and the Indian Ocean, which you have to go through to get to the Persian Gulf. Now, they said, okay, I'm going to take this meter and I'm going to break it. I can, instead of having all these things like 12 inches and 3 feet and 7,000, say, whatever, I'm just going to break it in 10. So if I want a smaller piece, I'm going to break it in 10 parts, decimeters. And I can break that decimeter into 10 parts, a centimeter. And I can break that into 10 parts, a millimeter. And I can keep going 10. I can get 10 bigger, 10, 10, and 10, 10, and 10. So metric is a base 10 system. A base 10 system. Why would a base 10 system be easy to use? Well, one convention, but let's think, what is our counting system? The system you use in math. What is our counting system that we use in mathematics? Base what? Base 10. I mean, this is how we count, right? Most of us have 10 fingers and toes. Some more, some less. Oh, you guys laugh. Did you guys know this is recessive? This is a recessive gene. 10 fingers and toes is actually recessive. The dominant gene is 12. I know you learn in biology, dominant gene is going to happen. Well, what they don't really mention sometimes in biology is that how often does the dominant gene occur? How often does the dominant gene for 12 fingers and toes occur in human populations? Very few. And in Western countries, usually that last one is taken off because it doesn't work very well. In other words, when you move your little finger, it's what moves that one. But some places, a friend of mine, who actually is a doctor, just got back from Afghanistan. He's a Navy doctor. He just got back. He was with the Marines in Afghanistan. But I remember when we were younger, when we first got in the fleet, he sent me a picture of a girl in Thailand. He basically said, look at her hands. He took a picture of her hands. You know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. She had 12 fingers. And it's like you look at the picture, there's something wrong with this picture, and then you start counting.
Was she okay? Like, was she tripping?
She's really fine. I mean, like I said, it just the last finger doesn't really work very well. It kind of it's like when you move your little finger, it moves that one, so it doesn't work very well, which is why it's taken off. But it's a recessive. But we're base 10. We're base 10. We like 10. 10 is good. We don't like 16. We don't like 2. We like 10. Things like that. Now, remember also those little prefixes. Now we'll talk about other prefixes. Another point. But things like milli, I know. When I first learned it, I heard milli. Milli, that sounds like a million. Why isn't it a million? Why aren't there a million millimeters in a meter? Well, because it's not English. Remember, these words come from French. Mil in French is 1,000. Milli, 1,000. Centi, cent. Same word we get our word cent from. Centi, 100. Remember, 100 cents, 100 centimeters in a meter, centiliters, things like that. So keep in mind, every one of those words actually stands for a power of 10. I mean, when you say centi, 10 to the minus second. Whatever is going on here is 10 to the minus second. Things like that. Now, from length, we get a volume. Now, there is no SI unit of volume. Now, when we start looking at some of our other units, things like, we have like force is measured in newtons. When you say newton, you're really saying a kilogram meter per second squared. But you want to say kilogram meter per second squared, kilogram meter per second squared, kilogram meter per second squared. It's all. We call it a newton. We call it newton. So, but those are the SI dimensions. There is no SI unit of volume. Our proper physics unit of volume is actually the meter cubed. But volume comes from length. Comes from length. And remember, this is a complete system. A complete system. So these guys said, hey, we're going to take a box. We're going to take a box here. And we're going to take a box of 1 centimeter by 1 centimeter by 1 centimeter. And its volume, that means its height, its length, its width, 1 centimeter cubed. So if I have a 1 cubic centimeter box, a 1 cubic centimeter box, I'm going to say that that 1 cubic centimeter box is 1 milliliter. That is a milliliter. A little tiny box. And to get an idea, basically take your fingernail, I made a box out of your fingernail, that's basically a milliliter. Maybe a little smaller, that's half your fingernail. Not very much. Think about volume though. We started to think, okay, well, here's centi. If I want to get to liter, 100, right? 100 centimeters to a meter, 100 centimeters cubed to a liter. It's volume. Milliliter. Well, let's think milliliter. So how many milliliters are going to be in a liter? Well, milli means 1,000, so it's going to be 1,000. So if we go up our next thing, our 1 liter is 1,000 milliliters, which means, well, if I have 1,000 milliliters, I must have 1,000 cubic centimeters, but it's cubed, right? We could really write this as 1 cubed, right? So something cubed is 1,000. What number cubed is 1,000? 10. So it'd be 10. Be 10. So in other words, 10 centimeters times 10 centimeters times 10 centimeters equals 1,000. By the way, what is the unit for 10 centimeters? What do we call that? That would be the big number. Anybody know what that is? 10 centimeters is 1 decimeter. So 1 cubic decimeter is a liter. I mention this because you sometimes see this in units, the cubic decimeter. Those of you in chemistry probably saw this too, because a lot of times units, instead of saying liter, they say cubic decimeter, because we don't usually use the liter in terms of our volumes. We don't say that. So a cubic decimeter on that. Cubic decimeter. But this still isn't our unit for volume. Our unit, this is our SI, this is actually our physics unit of volume. In physics, all volumes are measured in meters cubed. Meters cubed, which is actually 1,000 liters, or a kiloliter. Think of this is 500 bottles of soda. The cubic meter. So you have the little tiny box, which is the milliliter. A decimeter is about this big. You had a box about this big. This is about like this. Is a decimeter cube. So 1,000 of those would fill a box a meter cube. Now that's a lot. Meter cubed, if you have a meter cubed of anything, that's a lot of volume. Oh, that's best of the mark. But to give you an idea in nature, a couple of weeks ago I was listening, because they've been talking about Yosemite. If you listen to about Yosemite, they've actually had a lot of people have had accidental death in Yosemite. It's like one of their highest years. Well, they're talking about these guys who actually went over like 3 barriers to go next to the falls, and lo and behold, they went over the falls. But they're saying that they're talking about cubic yards. Now, a cubic yard is almost as big as a cubic meter. So we're talking those 500 bottles. They're saying there are 1,000 cubic yards of water going over the falls of Yosemite per second. So that's 50,000. 500,000 bottles of soda going over the falls every second. Something like that. 50,000 bottles of soda going over the falls every second. 50,000 bottles of soda every second going over the falls of Yosemite. A lot of water? It's a lot of water. Those aren't that big of falls. If you've ever been up to Yosemite, they're very narrow. They're not that. It's what waterfalls go. You go someplace like Niagara Falls. There's a lot more water going over Niagara Falls than there. So that's our volume. Volume. Now from volume, we're going to get mass. And so if I have something, so if I want to buy something, right? I want to know how big my container, but I might want to buy a certain volume of wheat. But most things are not sold by volume. You know that? When you buy cereal, is it sold by how big the box is, or how much mass is in the box? How much is the box? Because it's weight. Because things settle. Settle things like that. So we deal with mass. Now you might say weight, and we're going to learn that weight and mass do have a relationship. But weight is a force, and it depends on where you are. In other words, if you weigh 100 pounds on Earth, you'd be at 16 pounds on the Moon. You weigh 300 pounds on Jupiter. But your mass would always be the same, because mass has to do with how much matter is in you. That never changes on that. So we need to know about mass. And mass is based on a certain volume of water at a certain temperature. Now, why would they choose water? Why would these guys choose water? It's basic. Also, is it hard to get? No, it's everywhere. So it's not like they had to work at getting the water. But it's not just water. Now, the water they use, actually, do have to work a little bit. It's pure water. Pure water. And that's not what comes out of the tap. What comes out of the tap is not pure water. You have fresh water out of the tap. It has some minerals, it has some chemicals on that. But that certain temperature is 4 degrees Celsius. 4 degrees Celsius. Anyone know what is the significance? What property of water is at a maximum at 4 degrees Celsius? Anybody know? Pardon? Of the oxygen. Has to do with things floating. Pressure, you're getting close. Water is densest at 4 degrees Celsius. By the way, water is still a liquid at 4 degrees. This is why ice floats. This is a unique property of water. No other substance other than water does the solid float on the liquid form. Nothing else. It's one of the many unique properties of water. Water is the most unique substance in the universe. Water does things that no other substance does. It has a set of properties that there's no other. Yes?
Soda.
Well, soda is mostly water.
Oh, yeah. Like, it's like a different one.
The small impurities in there are not going to make a lot of difference. Most things we drink are predominantly water. I mean, depending on how much solid. You even things like milk, things like that. If you boiled away all the water, you're left with a little bit of solid, mostly water on that. So it's the water. But water is densest. The next semester when we deal with thermodynamics, we will learn why water gets dense, things like that. Which means you float. Which means, what can I say? The USS Missouri here. What can I say about its density compared to the density of seawater? It's less. How do we know it's less? It floats. Yeah, the USS Missouri, it floats. Aircraft carriers are less dense than water because they float. Most of a ship is, you look at it, so you see a lot of steel, but if you go on the inside, there's a whole lot of air. Mostly air on the inside on that. So we have density, and this density. So what they did is they said, okay, we're going to take 1 milliliter of this pure water at 4 degrees C. By the way, another way to write cubic centimeter is cc. You may have seen that, like your medicines. They'll say, okay, we want to give you 100 cc's of this medicine. Cc stands for cubic centimeter, milliliter. Medicine you get from the doctor is usually administered in terms of milliliters or cubic centimeters. Over-the-counter drugs, they use teaspoons. Again, it's that one of those crazy things like how many teaspoons in a tablespoon in a... That's why I'm a bad baker. Believe it or not, you think as a scientist that I could bake. I cannot bake. My case come up lopsided. My wife, great baker. But I cook. We should. She's a better baker than I am. I'm a better cook. Yeah. Well, I'm more willing to try the big things. It's like, if we cook turkey, I cook the turkey and the barbecue, and I do the slow cooking stuff. And although she makes a mean slow cooker chili. Love her chili. Much better than mine. So we have this math. So this is what a gram is. So I have 1 milliliter of pure 4 degrees Celsius H2O. That will have a mass of 1 gram. It's an arbitrary thing. Now it is arbitrary. They can use anything. Could they use gold as their standard? Yeah. Use anything as their standard, which is water. Now, and balance is just that. We use electronic balances, but remember, a balance is just what it says it is. You have 2 little pans, and you put whatever you want on this side, and you put your known little masses on the other side. When they balance, you know there's mass. The thing is, that works anywhere where there's gravity. It doesn't work too well in space, in the orbit, when there's 0 G. But there's gravity. It doesn't matter where I take the balance. If I had 1 kilogram on the Earth, it would still be 1 kilogram on the Moon. It would still be 1 kilogram on Jupiter. It would be only 1 kilogram on some planet around some star 5,000 light years away. Kilogram is kilogram. Okay? Weight's going to change. And we'll learn more about that. It's chapter 4. Okay? On that. So questions? Questions? All right. So we are going to do our exercise. We're going to do a little measurement exercise here. And probably we're going to get done. You guys are going to have time to start your homework on that. But just make sure every group, basically you need a book. So hopefully at least one person in every group has a book. What you do need to do is go up and one person in your group grab a ruler, and you're going to need your calculator. So if you didn't get your calculator out, please go get your calculator. Now we use our calculators every day. At least one person in the group hopefully has a calculator. One person in the group, that's good. One person on that. There, this will get to be done in your notes. One ruler for the group. All right, so we have a problem. Actually, we have 2 problems. We always start with a problem. It's scientific method. We start with a problem. It is a question. In our labs, it's always going to be a question. You need to copy down that question. And we actually have two questions. Okay, number one. You can just continue from where you are. And you basically want to call this, you can call this the page exercise. This is the page exercise. How thick is one page of your book in centimeters? Question, how thick is one page of your book in centimeters? Now, obviously, looking at your ruler, you are not going to use that ruler to measure one page. Well, we have to do something else. Now, the second question, based on part one, how many pages in your book? Now, the second one, you say, well, Mr. Reese, I can just look at the end of the book. That's true. But do you know that all the page numbers were put in properly? For all you know, maybe every page number with a 3 was omitted. Maybe if you really look at the book closely, the L numbers 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 14, 15, 16, 17. Maybe every time they got to a 3, they omitted it. It's done by computer. By the way, page numbers are kind of a new convention. You know, they've been around a long time. You know, there are a lot of books. You get some old books, there's no page numbers in them. You know, you have to kind of look how. It's like that information is 2 inches down through that book. On that. So everybody should write this down in your notes, right? Everybody write down. And you can go all the way across. You don't necessarily have to be just in that one little margin. You can write. We do exercises. Kind of use your judgment how you do that. You don't have to necessarily follow that strict Cornell style because we're doing something different. Cornell style is really for the notes. Although we put the exercises in the notes, you don't have to follow that on that. So, we start with hypothesis. We're only going to deal with part 1. So we can't deal with part 2 until I know the answer for part 1, right? So we'll deal with the second question in a moment. So our first hypothesis. And a hypothesis is the answer to that problem. And it's just a statement. In this case, the page in the book, or actually I should probably say a page in the book is blank centimeters, period. What you guys are going to do is write that in. Look at your ruler, look at the page, and try to think how big that is. Now keep in mind, now we're dealing with this side of the ruler, right? We're dealing with the 30, with the side that goes 30. Those are centimeters. Little lines are the millimeters, so 0.1 centimeters. So each line in there is a 0.1 centimeter. So think about, if it was between two of those marks, little marks, it'd be 0.1 centimeters. How much between the mark is that? So it's probably 0.0 something, 0.00 something is what your guess is. By the way, do you get it wrong if you get the wrong hypothesis? Do you grade it down? No. Now, if you don't explain to me why it's wrong, do you get graded down? Yeah. What if you get it right and don't explain to me? Do you get graded down? Yeah, regardless if you're right or wrong, you still have to explain why it's right or wrong. That's the most important thing in the end. It's not whether this was right or wrong, it's whether you can explain it. So everybody write down this hypothesis and put in your value. Talk with your group, right? Remember, the person behind you is also in your group. Madison might be a good resource on this. All right, so now we need to take some observations. And remember, so I need to know, one, well, I can't really measure the thickness of one piece of paper, can I? So I'm probably going to have to do a bunch. Now, I could do the whole book, but then if I trade the whole length, I would then have to count what? I'd have to count every single page. That'd be a little tedious and a little waste of time. So I'm going to take a chunk, right? I'm going to take a little chunk of that. So I'm going to measure the thickness of a chunk, right? But I'm also have to know how many pages are in that chunk. And because this is science, we don't usually just do one trial. We're actually going to do 2 trials. So you're going to do twice. Now what you want to do, so you're going to grab a chunk, and you don't want to do the end pages, because the end pages are kind of cardboardy. We just want to take the inner. You'll go over, grab a section like that. Make sure one person holds it very even, because if you let it tilt, it starts to angle. In other words, it's going to be longer than it really needs to be. You want to make sure it gets nice and square, so you probably don't want to lift it up too much. One person holds them nice and tight together, another person measures it. Then you need to count them. But it's a good idea to put something in there like a bookmark on either side, because after you measure it, you go like that. Uh-oh. Then you have to do it again. So it's a good idea to put maybe a bookmark on both sides so you know that page. Once you do that, take another section of the book. Don't do the same section twice. Do a couple different sections on that. Okay, so we're going to do that twice. So work together as a group. Remember, front table, turn around, work at the back table with your teammates. There are data tables, so they look the same. Data tables are for things you measure. Calculation tables are for math work. In this case, we have to think. Just to also think about our answers. Since we want page, are we expecting a large or a small number? Very small. So if I multiply the 2 numbers together, the 2 values together, page number of pages, and the thickness, the things, am I going to end up with a small number? Probably not. Number of pages divided by the thickness, can you give me a small number? Yeah. A smaller number, but not very small. So the other way, thickness divided by the number of pages. That's probably going to give you your number. So that's what we're going to do. So the thickness of one page is going to equal the thickness of the chunk you took, which is in centimeters, because that's what we want, centimeters, divided by the number of pages. You know, that's a page. Because at the end, we want to know how many centimeters per page, right? That's really what we're looking at, how many centimeters per page. And so, one page thickness, so our new table, we have our first trial, we have a second trial, and any time we take a trial, we take an average. So remember, add them up, divide by 2. By the way, common mistake with averages is to add this one plus that one, then go divide by 2. And you end up with the wrong answer. Why? Because you really took this one plus half of that one. It's that order of operation thing. So make sure you hit equals, this one plus that one equals, then divide by 2. Okay, on that. By the way, as a check, averages. Should your average ever be bigger than the largest value you have? Should it ever be smaller than the lowest? So if your average is not in between your values, somewhere in the middle, you did something wrong. Okay, so that's a check. It should be somewhere in between. All right, so let's calculate these things. It should only take you maybe about 3 minutes to do these 2 calculations to get the thickness and the average. Thickness and the average. Now we can address the second part of this problem. Remember, our second problem was how many pages are in the book? All right? So our second hypothesis. That second hypothesis. There are blank pages in the book. So you want to look at your data, what you collected, you know, how many pages and thickness of one page, and estimate how many pages do you think are in the book. So we need to write down our hypothesis. I need you to fill in the blank with how many pages you think, based on your data, that there are. Guys, eyes. All right, so this time you're going to measure all the pages, and one of the best ways to do that is you just hold them straight up. Make sure they're held straight up, nice and squares. One person holds it. And you're going to measure the thickness of the whole thing. But this time we're going to do 3 trials. But not only that, I want each person in your group to take a trial. So if you have 3 people in your group, if you have 4, 3 of you will do it. But each trial should be done by a different person. We're going to do each trial by a different person. All right? So we'll take about 3 to 4 minutes here. Get those 3 data points. The 3 data points there. Okay, so now we want to take our calculation. So we want number of pages. Now we already know how the thickness of one page, and we know the thickness of all the pages. So am I going to multiply or divide? Is the thing we're going to do multiplication or division? Because we want bigger number or smaller number? Bigger number, right? We want to end up with a bigger number. So if I multiply that little tiny number times the thickness of the page, I'm going to end up with a little tiny number. So it's not that. If I divide the little tiny number by the bigger number, I'm going to get an even tinier number. So again, even if I'm not understanding mathematics, I know I have to get a bigger number. And the only way I can get that is if I take the thickness of the book, thickness, which is in centimeters, divided by 1 page, which is that centimeters per page. And what happens is I end up with number of pages. So again, we have that calculation. So we have 1, 2, 3, and you're going to take your average. All right, so let's all calculate that out. Let me keep that out of my mouth. All right, eyes on me. I don't know if everybody is quite done, but eyes on me. Once you have this answer, so you have the number of pages, that average value, what you want to do is look at the back of the book. How well did you come out? Then you can write your conclusion. Okay, so you have a conclusion, and your conclusion sheet basically is address the hypothesis. Were you correct? Were your hypotheses correct or incorrect? Why? Give evidence. You should talk a little bit about how you did the lab. So a good paragraph, which means probably 3, 4, 5 sentences to that paragraph. Once you finish that, you can do, after that will be your daily summary. Every time we finish Cornell Notes, we do our daily summary. The daily summary is not the same as your conclusion, because your summary is just the high points of what did you learn in our lecture, in our lab, in our little exercise. And then you can put your notes away, and then all the rulers can go back there. Once you get that all done in your notes, you all write your own conclusion. Once you get that all done, you guys can get started on your homework. Should be able to at least get the first part of your homework done. Yes, sir?
Is it okay if we use like paper, not pages, like 1, 2, instead of things? We might have come back. Do you want a number of pages, like sides, or actually?
Well, yeah, it should be number of pages, which is going to be half the number of what says there, right?
Okay,
because if there's 600 pages, but how many pieces of paper are in there? In a 600-page book, there are only 300 pieces of paper, right? There is kind of why we duplex things. 6 have as many pages of paper. Okay, one thing. Okay, so how'd you guys do? How close did you come up? Did you come up pretty close? Doesn't matter. I think, how many pages of the book? 400 so much pages, isn't it? No. 723 pages, so that's like 360 pieces of paper. You got 350? That's pretty close. I mean, let's think about it. You're within about 10, 12, man. Think about how thick are 10 or 12 pieces of paper?
Oh, yeah. That's actually pretty good.
So, yes.
I thought I'd seen all that.
Yeah, so you're coming up pretty close. I mean, if you can get within about 40 or 50 pages, or within about 20 or 30 pieces of paper, you're probably doing pretty good, because it's not very thick. Okay, the idea of this, the whole idea of this was to get back into measuring things and try to be as accurate as possible. Because accurate measurement, you'd be surprised, in a lot of our labs, we are measuring relationships. And if you're not being accurate in your measurements, all of a sudden you end up with this graph that looks like someone just kind of threw dots on it. It makes no sense whatsoever. So you've got to be very careful in how you do this. All right, so write your conclusions. Put your daily summaries. You can put your notes away. Remember, I do collect it on test days when I collect the notes. Then you can get started your homework. Chapter 1 Chapter 1. All right? On that. And you had a hand up back here. There's a hand up back here, someone in the back. Did I answer your question? No. We're in the last 20 minutes of class.
Yeah.
Yes, ma'am. What? Just this section. Some of them keep it in. You should only have the current work. All the old work you get at home, so you don't lose it. So if you lose your book, so if you lose your backpack, you don't lose all. You'd be surprised. I've never lost a backpack.
I got stolen at football. Why not?